Right, so yesterday we looked at trig integrals. Now we're going to look at integrals that we're going to turn into trig integrals by using trig substitutions. And where they're really useful is to turn two terms into one term. Right, so in this case, if I've got a square root of a squared plus x squared, by turning it into a trig identity, I can make the a squared plus x squared into one term and then find the square root of it. So the trig identity we really want there is the 1 plus tan squared trig identity. So if we use the x equals a tan theta on that one, then I'll get a squared plus a squared tan squared, which would be a squared sec squared, and then the square root of that is a sec. So it simplifies it down to one term. If I had a squared minus x squared, which one would we want for that? We could use either sine or cosine for that one, right? Because we could go a squared minus a squared sine squared becomes a squared cos squared. Yeah, that becomes a cos. Whereas if it's x squared minus a squared, we'd want sec, wouldn't we? Because then we could turn it into sec squared minus 1. Yeah. So we get a squared sec squared minus a squared, which would be a squared tan squared. And then the square root of that is a tan. So that's the idea. So here we go. It is one of the, used to be one of the standard integrals, log of x plus the square root of x squared plus a squared. So this is how we would do it if we didn't know it. We'd say, all right, I've got the square root of a squared plus x squared. Let's turn this into a trig question. So I'll do x is a tan theta. So dx is a sec squared. Let's sub in. I get a sec squared on the square root of a squared plus a squared tan squared, but a squared plus a squared tan squared is a squared sec squared. The square root of a squared sec squared is a sec, which cancels with the a sec squared on the top, and we just simply have the integral of sec theta. And we saw yesterday the integral of sec theta is the log of sec plus tan. But now we need to get the x back in there. Well, tan theta is easy. That's just going to be x on a. To work out the sec theta, I'll just draw myself up a little triangle. I know tan theta is x on a, so opposite over adjacent. Pythagoras, surprise, surprise, the hypotenuse, look what it turns out to be. The same square root that we had in the original question. So now I can work out sec theta. The log of square root of a squared plus x squared over a plus x over a. Now you might remember I said the standard integral was just x plus the square root of x squared plus a squared. That's because I can use my log laws and go minus log a, but log a is just a constant. And so we can actually just get rid of those denominators and go, oh, well, it's x plus the square root of a squared plus x squared plus a constant. X on the square root of 1 minus x squared. Now, I'm not suggesting that you would use a trig substitution for this question, of course, because hopefully you've noticed it straight away that what we got there is, well, derivative on top, or close to the derivative on top. Okay. But if I didn't notice that, I'd say, all right, square root of 1 minus x squared. Let's do the substitution x equals sine theta. So dx is cos theta to theta. Sub in. The top becomes sine theta cos theta to theta. The bottom, square root of 1 minus sine squared. Well, 1 minus sine squared is cos squared. Square root of cos squared is cos, which will cancel with the cos on top, leaving me with just the integral of sine. Integral of sine is minus cos. Now let's substitute in. What do we know? Again, I'll just draw up a little triangle. I know the sine is x over 1. So then the third side, oh look, isn't that amazing? It's the square root of 1 minus x squared, which was the square root we had in the original question. So cosine adjacent over hypotenuse minus the square root of 1 minus x squared. Okay, square root of x squared plus 3. So the trig identity for this one, we want to turn the x squared into 3 tan squared, don't we? So x, in other words, is the square root of 3 tan theta. dx then would be the square root of 3 sec squared. Summing in, I get the square root of 3 sec theta. So that's what the square root turns into. times dx, which is root 3 sec squared theta to theta, 3 times the integral of sec cubed, and that's when we all start cheering, because sec cubed, yes, that's so much fun, sec cubed, if you remember from yesterday. So let's do it. Going to change sec cubed into sec times sec squared, integration by parts. U will be sec theta, to U sec theta tan theta, to V is sec squared, V is tan theta. So it now becomes 3 lots of uv, sec theta tan theta, minus 3 times the integral of sec theta tan squared. Sec theta tan squared. Change the tan squared, and we now get minus 3 sec cubed plus 3 sec. What have I done? Oh, I've just integrated the sec theta. Okay, so the sec theta became log of sec plus tan. Okay, I'm substituting back in best I can there, because I've now got my square root of x squared plus 3, which again now I can look at the first line and do it that way. So 2 lots of the square root of x squared plus 3 dx. Is that divide both sides by 2, and there we have our integral. But wait, I tidied up a little bit more, because I noticed in my log they're both on the square root of 3, which is just a constant, so it looks a little bit neater. I just got rid of that. Do you have to do that there? No, you probably don't. It just looks better. All right, we shall do half a jolly good fellow.